Okay, so this is lesson 4, I believe, in climate change. Okay, so today's topic is quite fundamental. To talk about climate change, you must talk about the greenhouse effect. So the lesson today will examine the greenhouse effect in a lot more detail. We're going to look at some of the greenhouse gases, describe what the greenhouse effect is, how humans are contributing to the greenhouse effect, and also the ozone layer and its depletion. So first of all, to introduce the greenhouse effect, let's look at other planets. So as you learned in grade 9, Mercury is the closest planet to the sun, followed by Venus being the second closest. However, if you examine their surface temperatures, Mercury during the day has a temperature of about 430 degrees, very hot indeed, but Venus, being further away, actually has a higher surface temperature at 462. How does that make any sense? How can Venus be hotter than Mercury? Like, wouldn't the distance to the sun determine your temperature? And the farther you are to the sun, the colder your temperature. Well, generally, yes, that is an important factor, but Venus has something that Mercury does not, and that makes the difference. That's what makes Venus the hottest planet in the solar system. And that is the greenhouse effect. So Venus has a lot of gases. Carbon dioxide makes up 96% of its atmosphere. So Venus has extremely powerful greenhouse effect. Venus is able to trap the heat from the sun, whereas Mercury doesn't even have an atmosphere. So the heat does not really stay on the surface as well as does Venus. So this explains why, despite being further away, the greenhouse effect on Venus makes it #1 in the solar system in terms of temperature, outside of the sun, of course. So the greenhouse effect is basically gases in the atmosphere that absorbs infrared radiation. Okay, and this heats up the surface of your planet. So more greenhouse gas you have, the stronger your greenhouse effect is, and the warmer the temperature of your planet. So the Earth also has an atmosphere, and the greenhouse effect does work also on Earth. Now, the gases that do trap heat on Earth are the following. So you can see that there's carbon dioxide, water vapor, methane, ozone, and then nitrous oxide. So these 5 are the big natural greenhouse gases. The existence of these gases makes Earth a lot warmer than otherwise. Okay, so these are all greenhouse gases. You do need to know which gases are greenhouse gases, which aren't greenhouse gases. So the ones I listed here are the natural greenhouse gases. Make sure you know which ones they are. If we were to remove all the greenhouse gas, the average temperature of the Earth would be -15. Okay, right now it's about +15. So that makes a tremendous difference. So we can't live without the greenhouse effect. We're going to look at each of these greenhouse gases individually and something about every one of them. So starting with the most abundant, not the most abundant, the most famous one, carbon dioxide. That's the thing on the news. The world is worried about our carbon dioxide emissions because it is a great contributor to the greenhouse effect. It accounts for around 25%. Now, carbon dioxide is actually very low in the atmosphere. It is measured in parts per million. Parts per million simply means if you have 1 million particles, how many of those particles are the gases that you're talking about? And in percentages, it's 0.0385%. So that's ridiculously low. But even at a low concentration, it still has a significant effect on our climate. So don't be fooled by the low concentration. And also this is increasing faster than ever before. Before the Industrial Revolution, the greenhouse gas, the carbon dioxide in the atmosphere is only 280. It is now 385, right? And it will go up to the 400s in the near future. That is our climate projection. And that's why we are concerned. It is rising way too quickly. Now, the Industrial Revolution happened not so long ago. It's in the 1800s. The span of a human life, yeah, that's a long time ago. I don't think your grandparents are alive during that time. But on the scale of the age of the Earth, that is a fraction of a blink of an eye. So in a fraction of a moment, it's gone up by around 50%-ish. And that is scary fast. And so human activities, therefore, significantly increase the amount of carbon dioxide through our burning of fossil fuels. So that's CO2. Now, with CO2, there are processes that release carbon, and then there are processes that take carbon from the atmosphere. All right, and those are called carbon source and carbon sink. If you have a carbon source, such as burning or cellular respiration, you increase the amount of carbon dioxide. And the carbon sinks are the oceans, the forests, trees. They can take in carbon from the air via photosynthesis, and the oceans can dissolve carbon dioxide from the air. Right, so those are big sinks. And this in nature is kept at an equilibrium. This is supposed to be completely balanced so that it doesn't change. Now, unfortunately, human activities, they did change that balance. All right, so moving on with the next greenhouse gas.
I have a question.
Yes?
How does the ocean absorb carbon dioxide?
How does the ocean absorb carbon dioxide? Water will dissolve a gas. Water can dissolve carbon dioxide, making it carbonic acid. Does that answer your question?
Yes, thank you.
So yeah, in other words, the increase in the amount of carbon dioxide in the air also acidifies oceans. Because when carbon dioxide is mixed with water, you make H2CO3, which is carbonic acid. So yeah, ocean acidification is a byproduct of climate change, and that kills marine organisms. All right, so the biggest contributor to the greenhouse effect is not CO2, but water. Okay, that is 67% of the Earth's greenhouse effect. That's 2/3. We don't really concern ourselves with the amount of water vapor in the atmosphere. Now, the reason for that is water vapor is simply part of the water cycle that will rain down and then it will be collected into the air again. We are not actually releasing additional water vapor into the air. However, we are releasing additional carbon dioxide. So that's the key difference. Carbon doesn't really descend onto the earth like water does. So it's stuck in the air. So that accumulates, whereas water vapor does not. So that's, despite being 2/3, it does not pose a threat. However, over the long course of time, this can also be a problem. Now, we learned about feedback loops on Friday, and the water vapor, its greenhouse effect, exhibits a feedback loop. How it works is, well, excess water vapor in the air traps heat. Okay, that's the greenhouse effect. Now, if you trap heat, your planet becomes warmer. And if your planet is warmer, you evaporate more water. So you increase the amount of water vapor in the air. And guess what? That's increasing the greenhouse effect even further, trapping more heat, releasing more water vapor, thus increasing the temperature again, and so on and so on. So this is a vicious cycle. So another example of positive feedback loop. All right. So we should typically try to stop positive feedback loops. That typically goes crazy. Like Venus is an example of positive feedback loop and carbon dioxide. Additional carbon dioxide on Venus raises the temperature, which releases more carbon dioxide, which raises the temperature. So the runaway greenhouse effect made Venus a living hell. Now, we don't want this to happen on Earth. Right now, the greenhouse effect is just right. You don't want the Arctic to start melting. You don't want ocean to start vaporizing more water. You don't want the methane trapped in the permafrost to be released into the air. So all of those are potential runaway greenhouse effects that we need to avert. And that's why the international community, the scientists are trying to tell us, well, you know, there will be a point of no return. Don't hit that point. So we are currently on a trajectory to hit exactly that point.
Wait, Mr. Joe.
Yes.
Why don't we want the Arctic to freeze? I mean, to melt.
Okay, so we don't want the Arctic to melt for many reasons. One of the reasons is if the Arctic melts, you will have a lot more fresh water into the ocean, and that dilutes the salt of the ocean, and certain animals, certain fish species, they can only survive if the ocean salinity is just right. If it's too dilute, they will not survive. Okay, and another reason is that increases the amount of water in the ocean, and that rises the ocean. And if you're in a coastal city, you are at risk of flooding. Okay, so those are the two primary reasons why you don't want the Arctic to melt. And another one is if the Arctic melts, you lose more ice. And we learned that ice has high albedo, it reflects a lot of sunlight. So if you lose more ice, the Earth is now worse at reflecting sunlight, meaning that further contributes to the greenhouse effect, another positive feedback loop. So that warms the Earth even further, amplifying all the other greenhouse effects. Okay, so that's the last thing we want. And unfortunately, the Arctic is already melting. Ice has been thinner. The landmass covered by ice is now less. So yeah, ocean has already risen. There are flooding already in many coastal cities.
Oh, Mr. Zoe.
Mm-hmm.
What's his name? Hubert. His internet snapped, so I think you're gonna have to let him back into the Zoom meeting in a few minutes.
Oh, hold on. Yeah, so if you disconnect, yeah, I have to let you back in. Hold on. I don't see anyone in the waiting room. I don't see him.
He'll probably be in like a few minutes.
He said a truck snapped the cable or something. I don't know.
Okay. Well, just let me know when he's back.
Oh, are you recording this live stream?
Yes.
Okay. So then he can just watch it later.
Okay, so anyhow, methane is our next greenhouse gas. As I mentioned, there's a lot of methane in the permafrost in the Canadian tundra. And permafrost meaning that it should be forever frozen. Problem, the greenhouse effect is melting the permafrost, releasing the methane that is supposed to be trapped underground. And methane is a more powerful greenhouse gas than carbon dioxide. Specifically, it is 23 times, not percent, 23 times stronger than carbon dioxide when it comes to heat trapping abilities. All right. Luckily, though, we don't have nearly as much methane as carbon dioxide in the air. Now, the natural processes that can produce methane are basically swamps and bacteria. The bacteria in swamps and bacteria in, let's say, a landfill, they all produce methane. Bacteria also live in the guts of some animals like cows. Those are called ruminant animals. They also are a source of methane. When cows chew food, they would burp out methane, which is why eating a lot of beef, that means that you are contributing to a more intense greenhouse effect. If you cut down our consumption of beef, then you are helping, you are doing your part in mitigating the amount of methane released. Okay, so the consumption of beef in North America and Europe mostly drastically increases methane, which is a greenhouse gas. Now, some people question, so wait, what? Wouldn't that be the opposite? I've had a student in the past literally ask me, you know, if cows produce a lot of methane, shouldn't we eat more of them so there's less cows? Okay, it doesn't work that way. If you eat more cows, people will farm more cows, so that actually increases the amount of cows. If you actually reduce the amount of meat consumption, farmers will raise less cattle, which means actually less cows would exist on Earth. Okay, it has to do with supply and demand. Now, methane before the Industrial Revolution was 0.7 parts per million. Now it is 1.78. So it's more than doubled. Okay, so and it is currently still increasing. Now, here's another greenhouse gas. This is even stronger than methane. This one is 300 times more effective than carbon dioxide as a greenhouse gas. Now, again, luckily, we don't have a lot of nitrous oxide in the atmosphere, otherwise we're cooked. So before the industrial age, it was 0.27. Now it is 0.3. It's still, no, it rose, but not by a lot, okay? So still, we need to limit our amount of emissions of nitrous oxides, although that's not nearly as big of a problem as carbon dioxide and methane. Now, where do we get natural nitrous oxide? Again, bacteria in the soil, there's nothing we can do about that. So yeah, just make sure that we don't emit additional nitrous oxide. Plus that this is also a toxic gas. All right, so ozone in the stratosphere. This is something that we want, okay? We learned that we are in the troposphere. The layer above the troposphere is the stratosphere. Now, in that layer contains ozone, ozone being O3, 3 oxygens bonded together. What the ozone do is, what it does is it blocks ultraviolet radiation from the sun. It prevents the majority of ultraviolet radiation from reaching the ground. And we learned that ultraviolet radiation can induce cancer, especially skin cancer. So the ozone layer acts like a protective shield, which is a good thing. Now, here's how humans screwed this up. In the 1990s, there is a hole observed on the Antarctic continent, a hole in the ozone layer. Now, how did that happen? Well, it turns out in the 1960s, 70s, and 80s, humans have been using a lot of chlorofluorocarbons. Okay, in other words, CFC, a carbon bonded to fluorines and chlorines. Now, these are compounds that we used to use in refrigerators and air conditioners. It is a good coolant. Now, we didn't know that this was a problem, so a lot of people around the world, households, all have CFC emitting fridge and air conditioners. This accumulated in the atmosphere, and this reacts with the ozone. So if it reacts with the ozone, it will destroy the ozone, so creating a hole. And the governments around the world, after realizing this problem, have all unanimously banned the use of CFC. So we no longer have that. So problem solved, right? Well, no. Even if you ban it, the hole still remains. Okay, because CFC can act as like a catalyst for the decomposition of ozone. And it stays that way. It stays in the air for a long time. So even if you stop releasing it, it's going to take a while before that breaks down in the air and it wouldn't have any effect anymore.
So what
Good
is
news
the half-life for that? You know?
I don't remember. A few decades, I imagine. Because
that's bad.
A few decades is actually pretty short, but for our lifespan, that's pretty long. Yeah, the good news is it's not that long of a half-life, okay? Because we observe an increase in the amount of ozone in the atmosphere recently. Compared to that of 2000, the hole is getting smaller, right? Mainly because we stopped emitting it, and that is so slowly decomposing in the atmosphere. So in around 50 years or so, we expect our ozone layer to come back, like fully. But I don't think, I probably won't live to see that day. I might. It depends on my luck. You guys probably should live to see that day if nothing goes wrong. So, yeah, hopefully by then the ozone layer is fixed. Okay, so ozone is supposed to be a good thing. However, if it somehow gets on the ground, if it appears in the troposphere, that is bad. Okay, because in the troposphere, it is a greenhouse gas, and also it is a component of smog. That is a toxic gas because it is so reactant, it will react with the particles inside of your lungs. It is a lung irritant. So that is something that we don't want. We want the ozone to stay in the stratosphere, but once it descends, that would be terrible. All right, so that's the ozone. Any questions about that before we move on?
Yeah.
Mm-hmm.
How come the hole in the ozone layer was formed like on the South Pole if we're not like we're not inhabiting that?
Yeah, that's a good question. I'm not sure why it's on the South Pole. You would think it should be everywhere, but no, it's on the South Pole. So I don't know. Maybe somebody can search that up. Actually, I'm curious now. Any other questions? No? All right. Okay, so moving on to more greenhouse effect. So look at that chart. That graph suggests that all of the, well, most of the greenhouse gases that we mentioned, except CFC because we stopped that cold turkey, CO2, methane, and nitrous oxide, those are increasing exponentially. It is not increasing in a straight line. No, it is shooting up. Just like coronavirus cases, it is increasing exponentially. Now, that is not an accident. Usually growth is exponential. The human population also grows exponentially. So that poses a severe problem, right? Because of how quickly these are increasing. If that increase is very low and gradual, okay, plants and animals should be able to adapt. But because it is so sudden, we are unable, well, I mean the flora and fauna on Earth, most life will be unable to adapt to the quickly changed climate. And this sudden increase is basically due to human activity. Nature rarely has events that are this drastic, unless it's like an asteroid or a volcano. But yeah, human activities over the course of centuries have drastically accumulated these greenhouse gases. Now, which brings us to anthropogenic sources. So anthropogenic, as we may have mentioned before, means human source. So resulting from humans. There are natural greenhouse gases, and then there are anthropogenic greenhouse gases. That simply means humans release these, nothing to do with nature. Okay, a lot of these are overlapping, like carbon dioxide, methane, nitrous oxide, and CFC. Three of those, CO2, N2O, and CH4, those are also natural greenhouse gases. So nature will also produce these. It's just that humans are helping nature out. CFC is just anthropogenic. Nature will not produce CFCs, only humans would. Right, so these are the four anthropogenic greenhouse gases. You got to know which one is which. Okay, water is also a greenhouse gas, but it is not anthropogenic. Okay, humans don't really release a lot of water into the atmosphere. All right, so the combustion of fossil fuels like gasoline, coal, natural gas, that drastically increased carbon dioxide. Also, deforestation didn't help. If you cut down trees for whatever reasons, either to harvest the wood or to use the land for other purposes, if you remove carbon sinks, if you cut the trees, there are less trees to take carbon dioxide from the air. So indirectly, you are releasing carbon dioxide into the atmosphere. All right, so there are mostly two ways, mostly burning fossil fuel, and then also deforestation contributes as well. Okay, so that's how humans contribute to the increase in carbon dioxide. Increase in methane, well, farming of cattle is the #1 source. In the United States, cattle is a really popular food choice. Many of the agricultural land in the United States are used to farm cattle instead of growing other plants for food. So cattle takes a lot of space, and also they release a lot of methane, right? As well as landfills, bacteria that exist inside of garbage dumps, they will break down some of the trash and release part of the trash as methane. That is a byproduct of these the bacteria metabolism. So these activities release a lot of methane. Coal mining is the third one. If you mine coal, you extract methane from under the ground, and that releases as gas. So all of these activities contribute to climate change. And if we were to lower the amount of meat consumption, especially beef, lower our dependence on coal, and produce less garbage, all of which will contribute positively to a better climate. Okay, nitrous oxide is the next one. So a lot of nitrogen is being actively produced in the factories because farmers need nitrogen for their plants. So a lot of nitrous oxide emissions come from feeding of animals and plants using fertilizers. Okay, and a smaller contributor will be the burning of fossil fuel. If you burn coal, you're not just burning carbon. Coal is impure. It's mixed with other compounds as well. You release nitrogen and also sulfur into the air. Whereas, sulfur is not a greenhouse gas, but nitrogen is. So that would be a problem. And the last one we mentioned, CFCs, they leak out of refrigerators and air conditioning. We don't use that anymore. So we've stopped releasing this into the air, but the damage has already been done. There is now a hole. So compare pre-industrial levels to 2008. Okay, this infographics. This is quite old because the date is 2008. Now it's significantly higher. So pre-industrial revolution, you don't even have CFCs because we didn't invent that. Now, in 2008, we do. And also on the right, you see the half-lives of these. I'm sorry, not half-lives, their entire lifetimes. How long they will last in the atmosphere. All right, carbon can last for up to thousands of years, depending on your luck. If a plant captured you, then you're gone. But most carbon dioxide won't be captured by a plant, so that's why the number is so big. All right, so problem with the anthropogenic greenhouse effect. So there are two types of greenhouse effect. The normal natural greenhouse effect, the one that we absolutely need for our survival, the one that Earth has, that's not the problem. The problem is anthropogenic greenhouse effect. If we continue to release these greenhouse gases, we are enhancing the natural greenhouse effect. We're making it more potent. All right, so the effect will be amplified. The warming will drastically increase. The average global temperature is likely to rise by at least 2 degrees, which will have basically devastating effects on the ecosystem and even the economy and human health. Okay, so that's why we keep reassuring that we will lower our carbon emissions, despite the fact that most countries are not doing anything. Now, here is another feedback loop to make this even worse. Now, we are accumulating carbon dioxide in the air. Okay, so the greenhouse effect is enhanced global temperatures rise. As a result, more carbon will be released from carbon sinks, such as oceans. Right? If the oceans become warmer, they are less effective at dissolving gas. You can dissolve more gas if the water is cold. As temperature increases, less carbon will be dissolved in the ocean and released into the air. Similarly, higher temperature means higher risk of forest fires. There have been multiple forest fires in the past few years, like Brazil in the Amazon, also Australia this current year. So those are all partly due to the greenhouse effect. I can't say entirely. Australia mostly due to the greenhouse effect and climate change. So this releases more carbon into the atmosphere, which amplifies the greenhouse effect even more, which releases more carbon, more forest fires, more droughts. So this is basically another positive feedback loop. This only gets worse. We need to cut it out immediately, and that's what we're seeking to do. If only governments can work as efficiently to combat climate change as they are for the coronavirus, we wouldn't have this problem, but alas, that is not the case. All right, so this concludes the lesson for today. We basically just learned the greenhouse effect, what it is, what it does, what are the natural greenhouse gases, what are the anthropogenic greenhouse gases, where did it come from? All right, and potential feedback loops that will decimate the planet. Any other questions before we?
Mr. Zhou,
Yeah.
for about how long were we using like refrigerators and like that would leak that chemical? I forgot what it was called, but like.
For how long did we use it?
Yeah. For like
a couple of decades.
Oh, wow.
It was invented, I believe, in the 50s or 60s. I can't remember exactly, and that's been banned in the 90s.
Okay.
Yeah,
Mr. Joe?
Yeah.
I have one more question. I think you mentioned it before, but when is the assignment due? The one where we have to watch the video?
Friday.
This Friday?
No, next Friday. No, next Friday, actually. April the 9th, I believe, the Friday of that week.
Okay. Thank you.
You're welcome.
Wait, Mr. Joe,
Yes.
how come some planets don't have an atmosphere?
Okay, hold on.